So I will upload the videos. I thought the videos would be smaller, but it's about 40 MB, so I cannot upload it immediately. I am doing the trimming or cutting of the videos into two halves. So once I extracted the videos having files smaller than 50 MBs, then I can upload as part 1 and part 2. All right, I think we can continue. Yeah, so once I give you the video, I hope you can complete the tables. Now we will continue with what is called parabolic partial differential equation. What we have discussed was elliptic partial differential equation, by the way, because we have seen that in our classification of partial differential equation, we have seen that Laplace's equation has b square minus 4ac less than 0. So that was your elliptic partial differential equation. So now we will see the parabolic partial differential equations. Parabolic partial differential equation. So this is one of the example, one of the common equation, the partial differential equation, which is under this parabolic partial differential equation classification is your heat conduction equation. So let us write heat conduction equation in one dimension. Okay, heat conduction equation in 1D. So this will be del U upon del T alpha del square U upon del X square. This is 1D heat conduction equation. It describes the distribution of heat in one-dimensional system like a rod, right? It describes the distribution of heats in one-dimensional system. Now, here we are going to use what is called explicit method. There are other methods like implicit method, but we will skip that. That is not so as simple as this explicit method. So studying this explicit method is quite sufficient. This is most commonly used one, explicit method. So in this explicit method, we are going to use what is called forward difference. In explicit method, we are going to use forward difference to write your del U upon del T. So in order to write del U upon del T, we are going to use forward difference. Now, here in 1D means, let's say this is our Uij cell, Ui comma j cell, and towards the right side, adjacent to that, there is this cell called Ui plus 1 j cell, and towards the left side, there is this thing called Ui minus 1 j cell. So this is the interval is H. The interval is H, and this is along this we define the time exists. This is your x-axis 1D equation. So this is called your time axis 1D one-dimensional heat conduction equation. So one axis is the direction of this axis, or the 1D direction is your time your x-axis, and we can just define this time axis here. So the j index will define the time index. So Ui j plus 1. So this exists, let us call it the interval, the time interval as k. The x-axis, step size is h. The time interval or the step size along the time axis is k. So it's something like this. Along this direction is time, along this direction is x. Okay. So, so as I said, in this explicit method, we are going to use forward difference to write this del u upon del t, the time derivative. So what we're going to do is del u upon del t, the time derivative, using forward difference ui j plus 1 minus ui j upon k. Okay. So we use the forward difference to express the time derivative in u. So then again, similar to our previous calculation, we're going to use del square u upon del x square, as we're going to write del square u upon del x square as del u upon del x forward difference minus del u upon del x backward difference divided by h. And we can write this as, you all know this, u forward difference in x ui plus 1 j minus ui j upon h minus backward difference along x ui comma j minus ui minus 1 j upon h divided by h. So this will be ui plus 1 j minus 2 ui j minus into minus is plus ui minus 1 j upon a square del square u upon del x square. Okay. Del square u upon del x square. So this is how we are going to write your del square u upon del x square. Now we can write our time derivative like this, del square u upon del x square like this. So you substitute here in this one-dimensional heat equation. So once you substitute here in this one-dimensional heat equation, you can write the one-dimensional 1D heat equation using finite difference, using finite difference approach here. This will be like ui j plus 1 minus ui j divided by k equals to alpha ui plus 1 j minus 2 ui j plus ui minus 1 j divided by h square. Okay. So this will be you can express this as ui j plus 1 equals to alpha k upon h square into ui plus 1 j minus 2 ui j plus ui minus 1 j. This minus becomes, if you transfer the right hand side, this will be plus ui comma j. Okay, ui comma j. Now if you put gamma as alpha k upon h square as a certain constant gamma, you can write your ui j plus 1 as gamma ui plus 1 j minus 2 gamma ui j plus gamma ui minus 1 j plus ui j. So this will be gamma ui plus 1j plus 1 minus 2 gamma uij plus gamma ui minus 1j. So this formula which gives you uij plus 1 element value is called Bender-Smith's formula. Okay, this formula is called Bender-Smith's formula. So we are going to use this Bender-Smith's formula, which we obtained from this finite difference approach to solve your partial differential equations. That is 1D heat equation. Okay, so the problem we are going to discuss in this class is this: solve the boundary value problem, that is del u upon del t equals to del square u upon del x square subjected to u 0t equal to u 1t equals to 0, comma u x0 equals to sine pi x where x lies between 0 and 1 using Bender-Smith's method. Bender-Smith's method. Taking h step size along the x-axis as 0.2 and k equal to 0.02. Find all values of u for t equals to 0 to t equals to 0.06. Okay, so we are going to find all values of u for t equal to 0 to t equal to 0.06, and here the step size along the time axis is 0.02. The step size along the x-axis is 0.2. So x-axis lies between x boundary lies between 0 and 1. The boundary of x, one end of the boundary for x is 0, one end of the boundary for x is 1, and one end of the boundary for time is 0, t is 0, another end is t equal to 0.06, and the step size are 0.2 and 0.02 respectively. Now, in order to solve this, you have to first compare with the general 1D heat equation. So the general 1D heat equation was del u upon del t, alpha del square u upon del x square, right? So this was the general 1D heat equation. Now, if you compare this with the equation in the problem here, you see that your alpha value is here, alpha value is 1, right? Here alpha value is 1. So alpha is 1. And we know that h is 0.02. K is, h is 0.2. K is 0.02. Then your gamma will be, which is alpha k upon h square. This will be 1 into k is 0.02 upon 0.2. This will be your 0.5. Gamma is 0.5, right? So the boundary condition we have is that for all values of t, for all values of t, u is 0 for x equal to 0 and for x equal to 1. For x equal to 0 and for x equal to 1, u is 0. So let me write what does it mean here. So it's something like this. Let me write a certain kind of table. I think that is how we are going to solve. So let me write it like this. I will explain it in just a minute. So let's say this is your t exists. Let's say this is your x exists. So we start with x equal to 0. We start with x equal to 0 here. Then x plus h, that is the step size is 0.2, means 0.2. X plus 2h, x plus 2h, this will be 0.4 and 0.6, and x plus 3h, x plus 4h will be 0.8. You know that h value is 0.02. So x plus 5h will be 1. This will be x plus your 5h, this one. Okay, x value is 1 here. So and along the time exists, t is 0 here. Let's say t is 0. And what is the step size for t? Step size for t is 0.02. So we start with t equal to 0, and then t equal to 0. We start with t equal to 0. What happens is that t plus k, k is 0.02, means t plus k means this will become 0.02. After this will be 0.04. After this will be 0.06. Okay. Now, if you look at this boundary condition, u value is 0 for all t. U value, sorry, at x equal to 0, this means this is your x. At x equal to 0 for all time. At x equal to 0 for all t, u value is 0. At x equal to 0 for all t, u value is 0. So that means at x equal to 0 for all time, these are 0. Okay. At x equal to 0, for t equal to 0, it's 0. For t equal to 0.02 is 0. For t equal to 0.04 is 0. For t equal to 0.06 is 0. So the functional value of u is 0 for all time at x equal to 0. And at x equal to 1, at x equal to 1 for all t, at x equal to 1 for all values of t, u value is also 0. See, x equal to 1 for any values of t, u value is 0. So what does it mean? At x equal to 1, here x value is 1. Okay, so it's like initial value of x is 0, so 0 plus a, 0 plus 2 a, 0 plus 3 is like that. So at x equal to 1, the u value is 0 for all values of t. Now, that is the boundary condition with respect to x. Now, another boundary condition we have in our problem here is that u x 0, that is called initial condition. Okay, initial condition at initial time. U as a function of x 0 is sine pi x. So for all values of x lying between 0 and 1, for all values of x lying between 0 and 1, for all values of x lying between 0 and 1, at t equal to 0, u value is sine pi x. Okay, at t equal to 0, u value is sine pi x. So t equal to 0 is this line. So let us find out sine pi x. What is that? u x0 sine pi x, u x0 equals to sine pi x. For all values of x at t equal to 0, this is equal to sine pi x. Right. Now start with x equal to 0. So u00 will be sine pi into 0 will be sine 0 is 0. Now what is the next x? Next value of x is 0.2. So at x equal to 0.2, your u 0.20 will be sine 0.2 pi, sine 0.2 pi. So if you calculate sine 0.2 pi, this will be, you can use your calculator also here. This you will get it as 0. No, let me just calculate it. What exactly is sine? Yep, 0.2 pi. I can just Google it also. Sine 0.2 pi is 0.5878. Then x equal to 0.4. Look at this. The next x value is 0.4. Next is 0.6, 0.8. So at 1, this is 0. Okay. So u 0.40 will be sine 0.4 pi equal to 0. This. So if you do this, this is going to be, let me just Google it again. 0.4 sine 0.4 pi. This will be 0.9511. X equal to 0.6, u 0.60, sine 0.6 pi, sine 0.6 pi. Sine 0.6 pi also again is 0.9511. X equal to 0.8, u 0.80, still value of u, sine 0.8 pi. If you calculate this, this is 0.5878. So you can just put all these values. So for x equal to 0, it is 0. For x equal to 0.2, for x equal to 0.2, the functional value is 0.5878. 0.5878. And next is 0.9511, 0.9511, 0.9511, 0.5878, 0.5878. Now, so this is from the initial condition, this condition, and this condition, the boundary condition and the initial condition. From the boundary condition and the initial condition, you already have the values of the boundary as well as the values at t equal to 0. So this exists. This is for the t equal to 0. For all these points, t value is 0, right? So we have to find the remaining values of u, and for that we are going to use our finite difference approach, or our Bender-Smith's formula, Okay. So let us try to obtain this value here. Okay. In order to obtain this value, we are going to calculate this value using our formula. What is that? The formula we are going to use is simply uij. This is ui plus 1j. This is ui minus 1j. And this is ui j plus 1. So in order to calculate this uij plus 1, we are going to need this value and this value and this value. So that is uij plus 1 is given by Bender-Smith's formula, which is gamma ui plus 1 j plus 1 minus 2 gamma uij plus gamma ui minus 1 j. Okay, so this is your Bender-Smith's formula. So this gives you the value of uij plus 1. If you know the value of uij, ui plus 1j, ui minus 1j. Now, if you look at this table which I have drawn here, in order to obtain this value, the one I just put a tick mark here, you are going to need this uij, ui plus 1j, ui minus 1j value. So this, using these three values, I'm going to calculate this value here. All right, using the Bender-Smith's formula. And I have already seen here that my gamma here is 0.5. Now, if you look at this, if you take this as, let's say, uij, this as ui plus 1j, this will be ui minus 1j, this will be your uij plus 1. All right, uij plus 1, we are going to use Bender-Smith's formula. So let us put all these values. Uij plus 1, we are going to use that. Gamma is 0.5. 0.5 into ui plus 1j. What is ui plus 1j here? This will be 0.9511. 0.9511 and plus 1 minus 2 gamma, plus 1 minus 2 times gamma 0.5 uij. Your uij will be, uij in this case will be 0.5878. So 0.5878 plus gamma into ui minus 1j, plus gamma is 0.5 into ui minus 1j. I minus 1j is, ui minus 1j is 0 here. All right, so just put 0 here. And if you calculate this, we are going to get what is that, 0.4755. Yeah, so once we obtain this, we can fill up the table here. This will be 0.4755. Now let us try to obtain this value, this box, the value of your function at this particular space, particular cell. So in order to find this, you will consider this as your uij plus 1 cell, and you will consider this as your uij cell, and this will be your ui plus 1j cell, and this will be your uij minus 1 cell. So from the values of this, this, and this, you can calculate this value. And similarly, you can calculate this value, this box value, from the values of this, this, and this. You have to fill up this box. And from the value, in order to obtain this, you are going to need this value, you are going to need this value, this value. Then you will fill up all these values in this t equal to 0.02 rows. Once you have all these things, you can start by calculating this, this, and this, and then you can calculate this, this, and this, and this. So you can continue the process. So I will upload this video, and I hope you can finish up all the calculations so that you can find the values of the values of all u at all these cells, the values of u at all these cells. Okay, I'll stop now. I will upload this video also, and you can finish up these calculations. So if you do it yourself, I think you will have confidence and you will learn. All right, I will stop now.